Push that rock here with Simpson Math. Let's talk about inverse functions. To do that, we need to get a definition for the identity element. Oh, let's see if we can see the screen a little better. Okay, let's say E, not the number E, I'll just use E here. Let E be the identity element under some operation. Call it star. Well, then E star A is the same thing as A star E, and it always gives us out A. So E is an identity element if you do the operation and it doesn't change the other element. So an example from addition is 0 plus 2 is the same as 2 plus 0, which gives us 2. So therefore 0 is the identity element of addition. You guys are familiar with this. For multiplication, what would it be? What do you multiply by and not change? The thing you're multiplying. Here's an example from matrices, multiplication. If I'm multiplying 2 by 2 matrices, well then this matrix times 2, 7, negative 3, 4 is equal to 2, 7, negative 3, 4 times that matrix, and it gives out 2, 7, negative 3, 4. So this matrix with a diagonal of 1s and a diagonal of 0s is the identity matrix for 2 by 2 matrix multiplication. Another example, more relevant to our class, is f composed of just the variable x, or is equal to x composed of the function f. And it's just f of x. So f doesn't change, and so therefore x is the identity element in composition. Okay, we're ready for inverses now. Let's see, can I position the camera? So J is the inverse of K under the operation star if and only if J star K equals K star J equals the identity element. So if you perform the operation with two functions and you get the identity element, or two elements and you get the identity element, those two elements are inverses of one another. So in this case, J would be the inverse of K. We denote it this way with this superscript -1, and K would be the inverse of J. So we say J superscript -1. So this -1 notation as a superscript almost looks like an exponent. We'll talk about that in a second. But this superscript -1 actually just indicates the inverse. So examples. In addition, opposites are inverses. So 6 plus -6 is equal to -6 plus 6, which gives us the identity element 0 in addition. For multiplication, reciprocals are inverses. So 6 times 1 over 6 is equal to 1/6, 1 over 6 times 6, which gives us 1. So notice they were reciprocals of one another. So the inverse of 6 is 1/6 in multiplication, but the inverse of 6 in addition is -6. So warning, when you see this superscript -1, if we're talking inverses, it does not always mean 1 over the input. It only means that when we're talking about it as an exponent under the operation multiplication. If we're talking multiplication, which is generally what we're doing with real numbers, when we see this notation, 6 to the -1, well, that means 1/6, because we're generally talking multiplication. But in the context of this more advanced algebra class, sometimes this notation is referring to the inverse, and if we're not talking multiplication, you're not going to get reciprocals. So that's an important warning. Let's look at an example of inverses from function land. So here we have two functions that pass the horizontal line test, meaning well, they pass the vertical line test because they're functions, and they pass the horizontal line test, meaning that every y has only one unique x that gets mapped to it. It doesn't have several x's mapping to it. We'll talk more about that in a second. But here I have two functions. I'm going to compose f composed of g. That means I'm going to put g into the f function. So with this little x right here in the f function, I'm going to put the whole g in place. So I write the f function, the cubed root of the input plus 5, the cubed root of the input plus 5, but I put in g for the input. G is x cubed minus 5. but minus 5 and plus 5 add to 0, so I just have the cubed root of x cubed, which is x. Oh, that's the identity element under composition. So we put in G into F, and we got out the identity element. And that means that G and F are inverses, if it works the other way as well, which if we put F into G, then we see that we're putting this function into the input of G. So we're going to cube F. Well, F is the cubed root. So when you cube a cubed root, you just get the input. So we have x plus 5 minus 5. So we have x. And so we see, sure enough, indeed, we got the identity element out both times when we did the operation of composition. So that means that G is the inverse of F and F is the inverse of G under the operation of function composition. Now, we need to know how to get inverses. So here's how you get inverses. The fact that you're going to get out x gives us a clue. See, we put in the outputs of a function and got out the input. That means that inverses are going to interchange outputs and inputs. They're going to swatch the x's and y's. We're going to interchange the outputs for inputs and inputs for outputs. So we'll just do that. Here's a function, f of x. I graphed it over here to make sure it passes a horizontal line test. That's important. If you want your inverse to also be a function, maybe you can tell me why it has to pass the horizontal line test. Now that you know that the inverting a function is going to interchange its inputs and outputs. So the outputs are going to become the inputs. That's a hint. But anyway, I just checked to make sure it passes the horizontal line test because I wanted the inverse to also be a function. Now, the step-by-step process, since I know that the inputs and outputs are going to interchange, I rewrite my y's as x's. In other words, I'll go ahead and let my outputs be represented by the input notation. And I change my input notation to the output notation and change the x's to y's because I know that the inverse is going to interchange outputs and inputs. So I go ahead and do that. And now I'm going to solve for the output. So the first step is to multiply both sides by this denominator. So I multiply this by y plus 1 and it cancels and leaves me just the numerator. And I multiply this by y plus 1. Now I distribute the x and get xy plus x when I distribute. Now I'm trying to solve for y. So I need to get all the y's on the same side. I could move the xy over here. And if you did, you'll get an equivalent function. I'm going to move the 2y over here. So I move the 2y over by subtracting, and I move the x over here by subtracting. Now I have xy and 2y. I can't combine those. They're dissimilar terms, but I can factor out the common factor of a y. Notice they both have a y, so I'll factor out a y. That leaves me an x minus 2. And over here, I just have this 3 minus the x that I subtracted over. So I have y times the quantity x minus 2 equals this 3 minus x. So I'll just divide by x minus 2 to get y by itself. And so I solved for y, and it turns out this function here, and I can write it as a function, and I'll call it the inverse of f because that's what it is. It's the inverse of the function I started with. So, and here's the graph of it. Now notice, we were supposed to interchange the x and y's. Well, this graph went through 0, 3. It had a y-intercept of 0, 3. So the inverse should have an x-intercept of 3, 0, and it does. Oh, that's cool. The original function had an x-intercept of negative 3 halves, 0. So now I should have a y-intercept of 0, negative 3 halves on the graph of the inverse. And sure enough, if we look down here, we see that is true. Oh, y'all can't quite see. Yeah, I know. Okay, this is negative 3 halves, 0 is that x-intercept. And down here I have 0, negative 3 halves is the y-intercept on the inverse. So sure enough, we swatched all the outputs and inputs. And when we did this, so the step was rewrite it as y notation, then rewrite y's and x's as y's. Do all the proper algebra to solve for y, and you'll have the inverse. Very simple. Take your f of x, rewrite it as y, then interchange the y's and x's. Write y's as x's and x's as y's, then solve for your y, and you'll have the inverse function. Now, in context, what is an inverse function? Because we frequently use functions to model things. Like, for instance, here's a little cost function. If you know the number of hours that you're going to take at this small college, then you just multiply those number of hours by 94 and then add in 72 and you'll know your tuition. So this is an awfully inexpensive college. Maybe you should go there because it's only $94 per credit hour. And then the fees only add up to $72. Wow, this must have been back in the 70s. But anyway, so we have this function that maps the number of hours you're taking to the cost that you pay to take those hours of credit. So we rewrite c of x as y. We interchange y for x and x for y. Then we solve for y. So I subtract the 72, divide by 94, and I have the inverse function. So what is the inverse function? Well, it interchanges inputs and outputs. So now, instead of inputting the hours of credit, we are now outputting the hours of credit. Instead of outputting the tuition, we're inputting tuition. So now X represents the dollars of tuition paid. So maybe you're just looking at the receipt. You just have somebody's receipt and it tells you how many dollars of tuition they paid. And you want to know, I wonder how many hours of credit hours they're taking. Well, you use this function to figure that out. You input the amount of money on the receipt and you'll get out how many hours they are taking. Math made simple at Simpson Math.